Now today's topic, it is slightly not a regular topic as compared to the previous topics what we are dealing. Typically, though it is bridge inspection and maintenance, it will be mostly related with the higher end of the advanced maintenance or advanced inspection tools what is available, not very much in India, but outside India things are available. How the technology can be leveraged and how this inspection can be improved. See, the problem is nowadays, if you'll see, we started making bridge bigger, larger, more in number, and we don't have the trained staff which used to be earlier who can go climb on the bridge and do all sorts of inspection and other thing. Number of trains are more, so time available in between the train to inspect thoroughly is very less. Railway experience suggests that we try to use the rail or the bridge inspection vehicles. They are having a crane mounted on it and having a bucket so that people can go sit on it and go up and down, etc., and see all the structures very thoroughly. But the experience suggests that they were not very much could be used, and basically when they came, they become more or less like a useless device. We had made a lot of expenditure on those vehicles, but because of the paucity of the blocks, etc., it cannot be used. So the worldwide trend is that we have to have implementation or some advanced technique where person does not go and they are able to inspect and assess the condition of each and every bridge component. So today's topic is slightly on that line, and I request all the participants to please post your queries so that the query can be summarized, put together, and then we will take in between the gaps. So, as you know, I am Sharat Kumar Agarwal, Professor Bridge at IRICEN, and I am taking this webinar typically as a part of continuing training, long distance training from the IRICEN, because everyone is not able to come. So in that line, this webinar is continued. So what we are going to discuss today, advanced methods, technologies, and how it can be integrated to a ongoing inspection system or our maintenance system. So the last part of integration, it is very vaguely used, very vaguely covered, because it requires a lot of planning and how we can dovetail the technology. So before most of the webinar is concentrated on the methods and technologies. This picture, if you are able to see, it appears that somebody is trying to climb on a bridge, using a rope and risking his life and everything. This type of structures not be far away. It is the reality now. If anyone has seen the bridges which has been built in the USBRL projects, it's difficult to reach there. So here it has been seen that by rope, one person is climbing up and down on a bridge and try to assess each and every component of the bridge. It is really not possible nowadays. But yet, it will not be 100% ruled out. That is true. But it can be minimized. Another view, you can see that how it is difficult for someone to climb and do the inspection like that. There are various methods. So let's see what is the present scenario. We are aware that bridges are critical components of any transport sector, say the railway. And we are also aware that the stock of bridges are aging rapidly. If you see, almost more than 50% bridges in Indian Railway are beyond their original design life of say 80 years or 100 years. So that's a big problem. Increasing loads. Loading standard started with BGML, RBG, MBG, DFC and so on. So we are increasing the load also. Environmental stressors, climate change, increase in the temperature, increase in the high temperature or a low temperature, extremes, more rainfall. So apart from that, industrialization, other harmful gases, all those things are creating problem. Then evolving safety standards, where earthquake can come, we are keep on updating our codal provisions. Fatigue we were not knowing some 50 years back. Now fatigue is a problem. So like that, the safety standards, as we become wiser, safety standards are also becoming more stringent. So all those things requires urgent need for robust inspection and maintenance regime. Now, when we are having the less technologies, we are having the less number of the bridges, we are having the more and more person to go inspect individually and decide what can be done. Now everything has been reversed. So we have seen one of the traditional method of inspection. It is visual manual inspection, but it is severely challenged by the scale. Number of bridges are very high. Complexity, we are using the complex type of structures. Earlier we used to have simply beams and trusses. Now it is, you can say, the bowstring type of a structure, or it is cable stayed bridges, or it is suspension bridges. Many type of structures where we are using more and more of complex material or composite materials. And size of the bridges, all those things makes a lot of risk associated with for the inspectors as well as for the users. So what happened to industry? How the industry is responding? The worldwide industry is trying to evolve and trying to give the tools and method in the hands of the engineers so that it can use the inspection remotely. So a sort of, you can say, a technological revolution is going on, integrating advanced tools such as drones, artificial intelligence, structural health monitoring systems, non-destructive testing, robotics, digital twins, and then finally we need a sophisticated data management platform. All those things are now reality, which we used to think maybe a sort of, you say, a sci-fi movie where you see the artificial intelligence or some robot is moving around. Now it is no more a sci-fi movie, it is all available with us. So we have to evolve ourselves and we need to embrace the technological development. And I understand for a given organization, whether it is railway, highway, the given organization, it is not possible to develop these technology by themselves. Market is evolving, industry is evolving, technology is available. We need to invite, have some sample test cases, we satisfy, and then we can use the technology to our satisfaction. And when we do that thing, because everything is new, we don't know. So we need to facilitate them. We need the methods and how we are assessing the defects, what we know, that has to be integrated. And then finally, we need to make our system in such a way that it can be dovetailed in our system so that it can be utilized for further maintenance activities, not by just merely showcasing one or two technology at one or two bridges. So it requires a lot of effort. It may be not today, it may take another 5 or year or 10 years. But this is the beginning when we have to do and we have to integrate the technology with us. See, worldwide, different countries people are using. I have taken few case studies, though I will just name the case studies in a very brief, but from those case studies, these detail has been taken. A simple example, this is a Donghai Bridge in China. There they are using the drone. Now with the help of drone, they are trying to detect a crack. Now when the crack has been seen, the drone pilot will zoom it into that. He will highlight the area where it has to focus and capture, and it will take it. So it is not like that. Somebody will take a videography like in marriage, and later on he will take 2 or 3 days and give you, and you look into the mobile camera. It will check your facial image and then give you 10 number of photographs where you had been witness that movie. It is not like that. It is like the inspection where you are using drone as your eyes. Instead of going to the defect location, you are sending a drone and sitting at the shore or in the control room, you are able to focus at the defect area, zoom it, capture it. See, it is not only capturing the image. Today technology is such that it will able to measure the length and width of the defect. It is also possible to assess how much deep the defect is, such as these cracks. So, unless you are using the technology and train it, it will not able to give you the correct result. Today problem is that we are having so many number of service providers. They are not civil engineers. They don't understand the structure. They are merely a medium to take the photographs or the videograph, and then they submit to us. We are not expert in the video imaging. We are not expert in the using of those images. So both we are not sitting together, and that is how we are not able to utilize the technology. So need is that we need to sit along with them at the time of inspection and tell them what I want. They will not be left alone. Let's see another example. This is AI driven bridge inspection, and let's see. Let's see. So this is one of the example where you can see that with the use of drone, with the use of the pilot, and with the use of the person who understand where the defect is there, we are able to capture the defect, highlight the defect, and later on it will be we will be take and we will able to find out what are the problems. So if we simply say that the technology can relieve us from the process, no. It is relieving us from the pain of going to that particular location and measuring the data. So we need to join the hands with the technology and use them. Let's move further. Similarly, here you can see that there are large number of cracks everywhere on the surface. You can see the cracks in the masonry here, it is on the road surface, it is on the parapet. So many places cracks can be seen. Now all those cracks, unless it has been identified, it has been demarcated, it has been measured, it is not possible. So what is to be done? In the image, all the cracks will be marked. We will make a baseline. We will wait for the traffic to flow for another 6 months. Again, we will superimpose the image after 6 months and the older image, and then we can see what happened to the cracks, whether it has widened, whether it is elongated, or whether other defects further developed. If the number of the cracks and the area under the crack remain the same, there is no change in the crack, then we can safely say that these are the superficial cracks which are not creating the structural problem. So like that, we need to really go into that and we need to identify what are the areas and how we can use the technologies. Now the question is that how the entire system can be used. See, the 3D model of the bridge is to be generated. It is not the thing which can be simply copied from the AutoCAD sheet, or which can be simply image can be taken and pasted. No. See, if you had carefully noticed, when the drone has recorded the bridge data, there is large many number of the triangles and squares. All these triangles and squares are pinpointing hundreds and thousand points on the structure. The drone is taking all these 100 and 1000 points together. The camera used by drones, they are having a 5 views: central view, upward view, left view, right view, down view, and all these type of views, they will be merged together to give you a three-dimensional image. Likewise, suppose we are using the LiDAR, we are using the photogrammetry, we are merging all the image in such a way that in the three-dimensional image, you will get all the data captured to realistic scale. It will not be 100% accurate, but it will be accurate up to few centimeters. Now, when this data and image is superimposed, if this data and image is superimposed with the structural drawings, then it is possible for us to make all these observations more accurately, correctly, and then the accuracy can also be increased to a large extent. When on this data, now as shown here, see, it is generated like so many spots on the bridge. Now it is an image. Now we are fusing both types. See, image is also a data. Data points are also data. They have to fuse together, and along with that, we give the correct dimensional accuracy from the structural drawing. When all the things are fused together, then it is giving you a very smart picture like this. In this picture, you can pinpoint the locations where you want to capture the defects and where you want to analyze. So it will go from the different view. Same structure, you see, they have been given in the different view, and also possibility is there. All the like tree is coming, or some persons are walking, or some vehicle is traveling across. If you want to eliminate all those things can be simply eliminated using the sophisticated softwares. Basically, this is not our job. This can be done by the experts who are developing these softwares and tools. So like that. So based on the data, they had finally made the 3D model. Of course, different type of software we may know the name, like Rivet is a name we know. Similarly, AutoCAD. These people are also now in the game, because they are into the process of giving the drawing, etc. They are into the game, so they can leverage their drawing experience with the latest technology. Let's see further. Now, if you see just an overview of what are the inspection methods. The bridge inspection and maintenance have evolved from periodic, manual, visual assessment to a data-driven, technology-enabled process. The primary objective are to ensure safety, optimized assets life, and minimize cost and disruption. Cost and disruptions, what you say that? Cost is, if we are not able to maintain the structure at the right time, the cost of maintenance will be very high, and if we further lag, then there will be a disruption in the flow of the traffic. If we are able to assess and we are able to baseline our structures, we are able to indicate what is the threshold value beyond which a warning is to be given. Then we can get early warning signs and we can take the remedial action as early as possible. These advanced methods can be integrated into comprehensive maintenance planning systems supported by cloud-based data management, regulatory compliances tools, and advanced analytics. It cannot be a very simple method. We have to use finite element analysis. We are required to use many number of sensors placed on the bridge. We may require to create the image using the drone, etc. Then we need to fuse everything together so that the the advantage of every method we brought together, fuse it, and then we are able to maintain, we are able to examine the structure more closely. Typical methods are visual and manual inspection. Definitely it will never be ruled out. You have to go to there. Non-destructive testing, you need to assess the structural strength or the material strength every now and then. Because of the environmental aggression, what is happening to a structure is it can be simply assessed on a superficial basis by the this type of digital inspections. But you need to go and make testing, maybe 100% non-destructive, maybe semi-destructive. All that type of thing you need to do and assess its material quality. Then the structural health monitoring system. You deploy a certain number of sensors and those sensors keep on capturing the behavior of a structure as and when the traffic is passing or whenever it is being aggressed by the environmental conditions, say high wind and earthquake. So all those things it will capture. Again, it will support the data with the FE analysis and then try to assess what happened because of that high stress environment. Then another item is robotics and autonomous systems. These are, unlike drone which are being piloted, these robotics we can leave is there. They are able to detect, move around the bridge and capture enough number of data. Like the crawlers. Nowadays you are using many robotics in the factory and workshops. They are basically fixed at a location, but once they are attached with the crawlers, they are attached with the moving wheels, they can walk around and roam on the bridges and they are able to capture it. Nowadays even the drones has come which are having the cup and section method. So it will stick to the bridge and then keep on investigating in much more detail and nearby like that. See, imagine it. We are getting the data from Mars. We are investigating the surface of Moon. Right, we send the robot there. Similarly, that technology, when it is used that far away in space, a smarter version or a lesser case, it can be used even on the Earth and on the bridge. I'm not telling that it is like in space science and technology, but I'm giving that a very far-fetched example in that way also. So it is being used. Yes, in India we are not very much, it's not happening that way, but abroad it is being done. Then AI-based image analysis. Just imagine it, when your structure is vibrating in a severe earthquake, we ourselves are able to visualize and see that the buildings are shaking, what is the typical movement of the structure left to right and top to bottom, etc. Now, if the same image is taken by a very or highly sensitive camera, which is able to take the frame in terms of microsecond or milliseconds, we are able to capture the image. Our capacity is 1/16th of second. That is our limitation. If anything is vibrating faster than 1/16th or more than 16 movement per second, we will not able to gauge it. We will skip it. Suppose it is vibrating 32 position in a second. We will skip alternate and we will only able to get the 16. 64 1/4. But if the camera, it is so advanced and it is able to take 6,400 images per second. Just imagine it. So what we are able to see with our bare eyes, it is going to take at least 4,000 times more pictures than we can see. If it can see that much, then it is able to assess what is the ambient vibration of a structure even the normal wind is blowing. With that ambient vibration, we will able to find out what is the modal frequency of the bridge. We will able to find out what are the different modes. We will able to find out what is the damping. And when it is coupled with the traffic movement on the bridge, we will able to find out how the stress is coming on the bridge. Now when it is coupled with some sort of sensor, then it is going furthermore. So that is what I am telling. AI based image analysis is highly advanced technique, but it is not far off. It can be done. Then finally is coming digital twin and bridge information modeling. Digital twin is what? When we combine all types of inspection techniques together, then we make replica of a bridge which is in the digital space. It is exactly the same as our bridge, having the same material property, because we are able to analyze it. When it is subjected to certain load or certain deformation, that data we can feed into that its digital twin, and that data will able to give us what is the stress and strain in the bridge, and accordingly we will able to say that how the bridge is behaving or how the bridge has already undergone such loading. What is the impact of that loading on the life of the bridge? So like that, we are able to do that thing, and these things are there. Now let's talk about these 4-5 items. Visual and manual inspections. Traditional hands-on assessment, often mandated by the regulations, remain essential for tactile evaluation and areas inaccessible to technology. Inside of the bridge, where drone cannot move, you can go there personally, put a mirror and see what is having a invert below the beam. If the drone cannot, but if you are having a crawler, it can go there. You are having a like you are doing the various types of testing inside the body. So yes, it is possible. Non-destructive testing techniques such as ultrasonic testing, GPR, infrared, thermography, eddy current, they are also allowing to some extent what is happened inside the structure and how the defect has propagated. Without opening, destructing the structures inside, we can able to find it out something. Structure health monitoring. Sensor network provide continuous or periodic data on structure performance, enabling early detection of the deterioration and predictive maintenance. Then robotic and autonomous system, drones, crawlers. Then robotic extend inspection capabilities to hazardous or inaccessible areas, improving safe and efficiencies. This type of thing is more common into your nuclear plants, thermal structures, or say the power stations where there are more danger to, we cannot breathe, we will be exposed to the hazardous gas or radioactivity, etc. But that can also be utilized when we are having the complicated cross section and inside or the access to that area we have partially closed. Then AI based image analysis, machine learning and deep learning algorithms automate defect detection, classification and trend analysis from visual and sensor data. All those things we are putting together, they are able to classify and do the trend analysis. So trend analysis is an important thing which will tell us that our structure today, it is in we are having the numerical rating system. If we are able to merge the numerical rating system with some sort of AI enabled or the data analytics system, then it is possible for us to classify the bridge, say it is coming in the sound condition or it is coming in the distress condition. They will able to do that. Algorithm need to be developed, and that algorithm can be developed based on the machine training to these structures. So we can say that yes, this type of crack is there. What is our feeling is that it can survive another 3 years. So we need to go for routine maintenance type of thing. It is not becoming immediate or still planned. Or if we say that yes, it is having a thing that it need to be a major repair type of thing, okay, 3 or 4 grading type of thing is there. But if we feel that it is like a planned maintenance or it requires so we can give that type of grading. So AI enabled system can give us the similar type of rating after doing a thorough investigation. Now, digital twin and bridge information modeling, visual replica of the bridge integrated geometrics, sensor and historical data for the holistic asset management and decision support. We have to take a call whether we have to rebuild the bridge or we have to strengthen the bridge or we have to replace certain component. All those things will able to get the information and from the digital twin things. Now let's go into detail of the various types of these advanced inspection techniques. Drones, UAVs for the bridge inspection. See, unmanned aerial vehicles, commonly known as the drone, have transformed the bridge inspection by providing rapid, safe and detailed visual assessment of complex structures. They are equipped with high resolution camera, thermal sensors, LiDAR. Drones can access hard to reach areas such as underside, towers, cables without the need of scaffolding or the lane closure. Here particularly high resolution camera, thermal sensor, LiDAR. These things are there. They will take a sharp image. They will able to assess if the crack is there in a structure, then it will not emit the enough energy. Plain surface emit the energy. So we need to understand what type of surface is there, and according to the surface we classify the thermal energy emitted, and accordingly we will able to say that. Then the LiDAR. From the LiDAR it is possible for us to measure the distance. We will able to see that what is the typical height, what is the typical depth, what are the area size, etc. We can able to capture with the help of LiDARs. Then recent innovation include suction cup drones capable of attaching to surface for close-up inspection, core sampling and sensor placements. So there are few companies, German-based companies are there. They are develop this type of drones. They can able to reach there. If we have already profiled what is the our structure, where the reinforcement or where we can make the holes. So these drone can go there. They can simply make the hole and place the sensor, close it. And if our sensor does not require any type of wiring, it can throw the data through the network. We will able to start capturing all sorts of information from those sensors. Drones can also be integrated with the GPR for subsurface defect detection and with the AI powered platform for automated image analysis. See, what I mean to say that none of the technology, they are able to do everything independently. We need to fuse various technologies together. So the advantage when we use the UAV for the bridge inspection, that accessibility and safety. Drone eliminate the need for inspectors to. So drone and UAV for the bridge inspection, advantage accessibility and safety. Drone eliminate the need for inspector to work at the heights or the over water, reducing the risk. And one more thing I should emphasize here. Whenever we are inspecting a structure and we have a fear or we see that there is a risk to our life, so we try to do the inspection as quickly and as fast as possible. Our half mind is occupied with the other side, for our safety. In that process, the inspection quality is greatly reduced. So that type of advantage is there. Then efficiency, you see that inspectors are completed in hours rather than days. See, what they had made some studies that with up to 75% reduction in time and 40% cost saving. This is again the data from the Western world. But one thing is important that somewhere I have seen that they are able to inspect 30-40 bridges. Slides again. 30-40 bridges in a day with the use of the drones, whereas they are able to capture that many number of bridges in a year when we do our manual inspections, given the same number of manpower, etc. So drones are helping us. Data quality, high resolution imagery and 3D modeling enable precise defect detection and measurement. Minimum disruption, drones operates without major traffic closure, preserving operation continuity. So these are the typical, you can say, the advantage of using drone. But yes, nothing is without some limitations. Regulatory constraints, airspace restrictions, especially near critical infrastructure, airport, can limit the deployment. Our data is going somewhere, so we need to find out how that data, location, etc. can be more safely handled. Weather sensitivity, wind, rain, fog, these type of limits the flight stability and the data quality. So yes, it cannot be done throughout the 24/7, 365 days or something like that. Battery life, flight duration is limited through the tethered drones, and the rapid battery replacement mitigate this issue. Thing is that drone can fly for few hours. If you want to fly for a large number of hours, it becomes bigger, costlier and heavier. So it cannot be used, and we are having a site limitation on the size also, so that it cannot create a problem for the structure. Therefore, all these things has to be done. But yes, it's not a big limitation, because again it can come back and it can be recharged and go, or we can replace the battery, it can go. Subsurface and tactile assessment, that cannot be done. Drone cannot perform tactile or subsurface inspection, necessitating complementary methods. तो जाके देखना तो पड़ेगा, लेकिन ये है कि आपको 10 जगह जाने की जगह हो सकता है एक जगह जाना पड़े. That type of advantage will be there. Now, some of the real world application and case studies. In that, few case studies are there. I have not gone too much into detail, and that can be, I think, be a part of the second or third lecture in the series. We can see that how each and every case study is there, because that will be too detailed. It is just an introductory. So there is a Golden Gate Bridge for the seismic retrofit in US. Drone inspected cable and anchors, reducing scaffolding need and the traffic disruptions. Otherwise, inspecting the anchor at the top of the tower, it's very difficult. Like I have shown you, somebody is putting a rope and climbing on the top, etc. Then San Francisco Oakland Bay Bridge replacement, LiDAR equipped with drone provided precise mapping for design and construction monitoring. The important point here is, all the inspection is not post construction. Many times we need the inspection while construction is going on for a precise construction. Nowadays, the more technology is there, we are using high-end software, we keep on reducing the size of the members, making it thinner, sleeker. Then the quality control and the exact size and shape become more and more important. So drone can help there also, like it has done in San Francisco Oakland Bay Bridge replacement. New River Gorge Bridge replacement, drone facilitated mapping and surveying, improving efficiency and reducing environment impact. Rewa, Waipuna and Grafton Bridge in New Zealand, AI-enabled drone captured thousands of images and acoustic data, enabling full photogrammetric modeling and defect mapping for the maintenance planning. कहां पे कब क्या करना है, कितना करना है, कितनी लाइफ है. Germany's autobahn bridges, drone-based digital twin and AI-driven damage analysis improved inspection accuracy and reduced manual labor as demonstrated in a pilot project with 20 and die autobahn. तो वहां पे उन्होंने करके एक सिस्टम क्रिएट कर लिया और उन्होंने मैनुअल लेबर को रिड्यूस किया. आज की डेट में हमारे पास भी ये सोचना गलत है. किसी समय ये सही था कि हमारे पास मैनुअल लेबर बहुत ज्यादा है. आज के समय में स्किल्ड मैन पावर नहीं मिल रहा है. कहीं ना कहीं हमें ऑटोमेटेड सिस्टम पे जाना पड़ेगा. Integration into maintenance planning. When we are using this type of cases, how this drone can be integrated? Drone data is processed using specialized software, often with AI assistance, to generate comprehensive report, 3D model, and maintenance recommendations. These outputs are archived for trend analysis and integrated into digital twin platform for ongoing asset management. As I told you already, they are not individually operated. There has to be a complete ecosystem. Now, another thing we can see, the AI-based image analysis and defect detection. What are the advantages? Let us first understand what are these basic principle behind the AI image analysis. AI-based image analysis leverages machine learning and deep learning algorithms to automate the detection, classification, and quantification of bridge defects from visual to sensor data. Lot many things which we miss during our visual inspection, all those things will be recorded and all those things can be deeply analyzed. Finer trends can be captured. Convolutional neural networks, YOLO, faster RCNN, and semantic segmentation models are widely used for crack detection, spalling, corrosion, and other anomalies. These are some names of the patented software techniques which are being used by the service providers. None I named is from India, like convolutional neural network, CNN, YOLO, you only look once, faster RCNN, etc. So they are based on some software technique which we, as such, we don't have. There may be something available in India also, or they can help us to use those things. AI model can process data from drones, ground-based camera, infrared tomography, infrared thermography, and GPR, enabling multimodal defect detection. So when we are able to capture the defect from several sources, we will able to confirm each and every we are able to confirm the different defects from the different sources, and then it is possible for us to be more specific and more accurate in the defect detection. And this AI-based system can transfer learning domain adoption and synthetic data generation, addresses challenges related to limited labeled database and environment variability. What it mean? That say the software has been trained, it has come for the first time in India, but it has already been trained certain data using either in US or in China or somewhere else. So it has got something in its mind It has got some history, some knowledge it is having, based on which it is able to tell us what is the most likely defect or most likely issues are there. When these things we are able to classify based on our own experience, then the data will automatically update itself, and then it is started slowly getting converging with the Indian defect pattern and Indian method of identifying the defects. So what are the advantages of this AI based image analysis and defect generation? High accuracy. AI model achieve up to 95% precision in defect detection with rapid inference time suitable for real-time analysis. Suppose a drone crack detection has been fully trained, and we know we are inspecting, we know which location this defect is there, what is the length is there. If we are able to monitor for some time at the same location, we will be able to see under passage of traffic whether the defect is live or not, and then the drone or the AI based system can able to classify it as a live defect. It is somewhere near the bearing area. It is able to reduce the cross section by 30% and something like that. So based on that, it may able to classify the defect, and then it is able to predict when it is going to fail. Automation reduces human error and subjectivity, enabling consistent assessment and continuous monitoring. It's not like the human being, we have to go and inspect in shifts and other thing. When the system is placed, the image is already available. We have integrated it with some sort of sensing or some sort of sensors. Change in pattern in the sensor data will immediately trigger the alarm. Predictive analysis support forecasting and of deterioration and proactive maintenance planning. We know how the temperature pattern is going, how the humidity is changing, and how the acidic gases in the environment is changing. If we put all the data together, synthesize, and we know how the concrete is reacting with this type of thing and how much depth of concrete is already carbonated, then we can predict, depending upon these data, how many further months it will take or year it will take to penetrate the entire cover and started corroding the reinforcement. If we know the reinforcement is already corroded from the image, like there are the brown patches wherever the reinforcement bar has been located using the reinforcement bar locator. Now we know that the corrosion has already set in the reinforcement, it has gone deep down it. We know when the structure was made, when we are inspecting today, how many years happened, and how the environment condition has been changed. So all those things we need to maintain, and then we can predict it. Okay, it will take another 5 years before the spalling takes place. We know the rate of corrosion, how the volume of the corroded steel will increasing. So all those things, if it is integrated together, it is going to give us. Again, as a caution, it all appears as if we are in a magic world, and by just purchasing one technology and clicking few buttons, it will be over. No, it will not. It will take time. Whether we do it ourselves, importing the technology partially, or we invite them to come and do all the job, still it will take time. Yes, if we start today, maybe after 5 years we'll get some fruit. If we don't start, then the things will deteriorate faster, and we will not able to take the action in time. So anyway, then scalability. The process large database from multiple sources facilitate network-wide assumptions. It is something like that. With the given capacity, if it is possible for us to inspect one bridge at a time or one bridge in a day, with the use of the multiple drones or with the use of the same drone, we will take at least few bridges in the same day. So scalability means our capacity to inspect more and more bridge will increase drastically. And when it increases, we are definitely able to ensure more and more safety. If we are able to repeat the inspection, which we used to do once in 5 years, we are able to repeat once in 2 years or once in 3 years or every year, say. In that case, we can make better prediction about the life of these structures. What are the limitations? Data quality and diversity. Require large, high quality and diverse database for training. False, positive, negative remains a challenge. Means the brown color can be paint, brown color can be rust mark. So it is very difficult for a simple image analysis whether it is a rusting. So we need to rely upon multiple sources of information. Complex scenario may struggle with complex geometrics, environmental noise and subtle defects. What are those things like? The shape and size of a structure is such that it is not easily perceived by the sensors or by the drones, etc. Then image will smudge together. Sharp edges may be lost. One or two component overlap each other. So that type of problem may be there. Explainability. Lack of transparency in AI decision making can hinder trust and regulatory acceptance. What is happening inside the brain of the machine we don't know. Unless any one of us is the author of that code. So what happened? Many of the service providers, they maintain the program and they try to keep that as a secret because their entire remuneration or their entire economics is depending upon the secrecy of the brain behind the software. If the same type of software is available to everyone, so anyone can use and may possible make a better one also. So the original software developer will lose the business. So that is how they really do not want it. So, but the problem is that if that type of thing is there, we also fail to trust. We also find it is difficult to trust because we don't know what is happening inside. Unfortunately, if we think we can master those software technology, we can go inside and do it, that is also not possible. By default, we are civil engineers and going into the software business and making the software is again very difficult for us. We need to understand that thing. We need to trust. The best way of developing the technology and trusting is to experience it, test it, and then say whether it is really working or not. We know what are the defects, what are the locations. So it can be done in that way. Computational resources, high performance hardware is needed for training and inference. Though edge computing is emerging as a solution, nowadays, yes, it is a problem. I agree, but nowadays computation is not an issue. High quality computer is not an issue. We cannot have every place in the entire our network, but we can have at certain locations. So the importance is there. We may think of establishing certain number of specialized areas where all these technologies data can be analyzed every time, and we can have the group of experts. Some of the real world application and case studies. To inspect Germany, AI-driven damage analysis achieved 88.6% accuracy in crack detection, streamlining data management and enabling predictive maintenance. Wollens engineer of USA, AI-powered digital twin reduces inspection time by 20% and labor cost by 10 to 15% for a stone arch and Robert Steele Street Bridge in Minnesota. So some saving they could able to see that. Donghai Bridge, China, drone mounted edge device perform real-time crack detection using You Only Look Once version 8 technology and Deep Lab version 3 plus technology, achieving high accuracy and rapid inference. Similarly, YOLO-based GPR analysis in USA, deep learning model trained on synthetic and real GPR data, automated reward detection, improving scalability and reducing the manual annotation needs. How it can be integrated? AI generated defect map, trend analysis and predictive models are integrated into digital twin platform and bridge management system, supporting data-driven decision making and prioritizing of maintenance actions. अगर हमें ये समझ में आ जाता है कि किस जगह पे क्या एक्शन कब लेना है, तो हम अपने सारे की सारी मेंटेनेंस को प्रायोरिटाइज कर सकते हैं. आज के दिन में भी हम अपना इंस्पेक्शन करते हैं, तो वी टेक सर्टेन कॉल इन द फील्ड बेस्ड ऑन आवर एक्सपीरियंस. नाउ वी नीड टू मेक द कंप्यूटर टू हैव आवर एक्सपीरियंस एंड टेक अ डिसीजन. Structural health monitoring, SHM systems and sensors. See, structural health monitoring is relatively and well-established term we understand. So, it is essentially a sensor-based system where we are having many number of sensors such as strain gauge, accelerometer, displacement transducer, temperature sensor, weigh in motion devices, and they can record or they can sense the structure continuously or periodically to monitor the structural performance of the bridge. Data is collected according to sensor, displacements, strain or the modal parameters, natural frequencies, damping ratios and the various environmental conditions. Advanced SHM framework integrates sensor data with the digital twin, finite element model and intelligent data system or the dashboards for anomaly detection. They can also do trend forecast and give us a visualization of the structural behavior. Now, what are the advantages? Continuous monitoring, and that enable early detection and deterioration and the support predictive maintenance. Data-driven decision making provides objective quantitative insight for the asset management. Integration with the digital twin enhances visualization, simulation and life cycle management. The limitations: installation and maintenance. Sensor deployment can be costly and complex, especially on the existing structure. Many times it required to adjust again and again. Many times it required to replace because of the environmental conditions. So this is a problem. So it does not mean that you install a sensor once and forget it. No, you need to periodically maintain the sensor system also. Data management. When we are doing the continuous data collection, so it becomes a huge data problem. The large volume of data requires robust storage, processing and cyber security measure because data goes in somebody's hand. Bandwidth and reliability. Wireless sensor network may face connectivity and power challenges. But it is not that it cannot be overcome. It can be overcome by having a sort of solar-based power supply, power backup, data backup, Data, as and when we are able to get the connectivity, we can send the packets of the data, or if all things are not possible, then we will have enough storage and we can go and replace the storage device periodically, maybe monthly, maybe 6 monthly, depending upon the volume of data and the size of a storage device. Some of the examples in India, somewhere the Belly Bridge integrated digital twin and sensor-based health monitoring framework enabled real-time assessment and predictive maintenance, reducing the inspection cost and preventing. Typically in the hilly areas, belly bridges are like you say bridges which are modular in shape and typically used where the regular construction of bridge is not possible. These are steel bridges. Senskin in Europe, dielectric elastomer resin sensors with wireless transmissions were piloted on the Bosporus and Ignatia motorway bridges, supporting decision support tool for maintenance. See, these are all the case studies, one type of thing which has been done and to evaluate and develop the technology. A smart patch, again Europe, conductive fiber strain gauges embedded in fabric provided multi-parameter monitoring, commercialized for bridge application. How it can be integrated into maintenance planning. The structural health monitoring data is used to calibrate finite element method models, inform maintenance scheduling, and support risk-based prioritization. Dashboard and decision support system visualize trend, anomalies, and recommend actions. We have to understand the behavior of the structure, and behavior of a structure we are monitoring throughout. And then on the background we are doing some of the simulation with respect to the structural analysis and FEM based type of thing. So it is like a feedback loop. Depending upon the initial structural FE model, we predict what is the displacement, we measure in the field, then we correct it, and then accordingly we change the material property, we change the end condition, we change the structural modeling, and accordingly we do it that. So it requires to continuous upgradation of the system, and then finally we are able to make a better judgment or analysis. So everything requires time. Non-destructive testing technique for the bridges. These are well known. So I think many people are taking a sigh of relief. At least something we know it. So it is the same thing with me also. So when we started preparing for today's webinar, many things I was also not aware. So many technological terms which elsewhere being used in the world, like common Indian, I am also not aware. So because I read it, I prepare it, so it may appear that I know something, but still we need to learn a lot. I just give you some name, some technology jargons, but how it is being done, what is the background, what is the limitations, all those things will help us to select a technology. Let's see that ultrasonic testing. It uses high frequency sound waves to detect interflow and measure thickness, typically for steel structures. It can also be used for concrete structure because of the heterogeneous nature of concrete. This puts some limitation on it. Phased array ultrasonic testing. Advanced ultrasonic testing with multiple transducer for volumetric imaging and precise defect sizing. The phased array is much advanced. Ground penetrating radar, electromagnetic pulse detection, rebar, voids, and delamination in concrete. Infrared thermography. Thermal imaging identifies subsurface defect by detecting temperature anomalies. If the surface is having a uniform temperature, somewhere there is a sharp change in the temperature, that indicates something is wrong. Then we can go and look more closely and find out what is the problem. Many times, a hollowness in a concrete can be easily detected by thermal imaging. Acoustic emission monitors stress waves from crack initiation and propagation. It is something like that. When any structure is subjected to loading, the tip of crack formed in the structure yields and crack length enhanced, or it become wider. When all these things is happening, at that particular instant, acoustic emission takes place. And that acoustic emission captured by the sensor, then it is possible because all the acoustic emission emitted from one particular source will travel in the structure, and the sensor will capture multiple number of the information, and accordingly it is possible for it to zero in which location what emission has taken place. Then eddy current testing, defect surface and near surface cracks in steel using the electromagnetic function. Many times it is helping us to check these structures. If there are subsurface defects, surface defects, yes, you can do DTP or something is there if you are accessible there, but if you already filled it with the paint, etc., it is not possible. Eddy current will able to detect that thing also. Radiography, X-ray or gamma ray imaging reveals internal primarily in steel structures, but because of the inherent health hazard of the radio waves, we are not very fond of using it. So even though technology is available, it is not being used. So what are the advantages? Internal defect detection identifies issues invisible to visual inspection, support early intervention, non-invasive, preserve structural integrity and minimize disruption. Quantitative, minimize disruption because one need to go there and take it. So the moment there is a human presence is there, we need to take certain related precautions. Then quantitative assessment provides measurable data for the defect characterization and trend analysis. Limitation, expertise required. Interpretation of NDT data can be complex and require a skilled operator. Many times it requires the skilled operator to be there and interpret rather than capture data and then in the lab or in the office somebody will tell. Again, equipment cost, advanced NDT tools like POUT and radiography are costly. Environmental sensitivity, moisture, temperature and material heterogeneity affect the result. Humidity is a problem. Temperature, yes, may change. If the temperature is increases, then the wave velocity inside the material also changes. Your electronic circuit will behave slightly different. All those things is having the problem. Yes, these are the limitations we need to keep in mind. Some books are also there. RDSO guidelines are also there. It covers the rebound hammer, pulse velocity, GPR, acoustic emission. Like that, sensor-based testing, etc. has been given. We can utilize them and apply for the case studies what we are looking into that. Federal Highway Association USA has published a document on the POUT and validate as an alternative to radiography for weld inspection with a strong correlation in the defect size and the location. It's a great thing. Italy, they had issued multi-scale NDT UT testing, eddy current, thermography combining together, assessed historical tie rod integrated result with the fracture mechanics for the safety evaluation. What I mean to say that the three different type of NDT testing, they correlate each other and then we are able to pinpoint the defect. China based, the drone based infrared thermometry and the AI segmentation enabled rapid accurate delamination detection on the bridge piers. NDT data is used to calibrate digital twin and FEM models, inform risk-based maintenance prioritization, and support regulatory compliance. Automated algorithm and AI model enhance data interpretation and reporting. So they give a very vital information. In fact, for age-old structure, it is always advised to use NDT or the partially destructive testing to validate the material property. Now let's talk about use of robotics and the autonomous crawlers for the bridge inspection. Robotic systems, they include crawlers, manipulators, and hybrid unmanned aerial vehicle crawler platform extend inspection capabilities to hazardous, confined, or complex areas of the bridges. These robots are equipped with cameras, sensors, and NDT tools for autonomous or remote controlled assessments. Now, many of us are using unmanned water vehicle to assess the underwater inspection. So again, I am selling that thing. Underwater inspection we are not able to do at all. So we now relied upon the underwater inspection using the robots. In aerial segment, because we are able to see that, so we still hesitate using the various inspecting methods other than the visual and self going there and inspecting it. So when underwater we can inspect, why not we can inspect in the aerial segment also? It's only a mindset which need to be changed. Recent innovation in the robotics and autonomous segment include suction cup drones, which I already told it, hybrid UAV that deploy crawlers for steel component inspection. Hybrid UAV means they can fly there, reach there, then attach it, and then they simply crawl on it or walk on the surface. So it's a mixed type of thing. The advantage of using robotics and autonomous crawlers: safety, minimizes human exposure to dangerous environment. First thing is that comprehensive coverage, accesses areas unreachable by manual or drone inspection. Because it is attached to surface, it is crawling on the surface, it can creep inside. Integration with AI and sensors enables automated defect detection and real-time data transmission. It captures the data, come away, and then send the data wirelessly. What are the limitations? Mobility constraints, navigating complex geometrics and confined space remain challenge. Whatever is the close, nothing can go inside. Then this robots or autonomous vehicle also cannot go inside. We need to create some space, something from these instrument can go, a larger hole at least, where it can crawl inside. Power and communication, battery life and wireless connectivity are the limitations. How to operate, how long to operate, and how the data is to be transferred. Cost is definitely high. High initial investment and maintenance requirement. It is not the maintenance of the bridge per se, it is the maintenance of these instruments also, the robots. So that itself adds to cost. That we need to really look into that. Some case studies, USA they say it birds. Missouri S&T Bridge Inspection Robot Deployment System integrates Bridge Inspection Robot Deployment System BIRDS. Integrate UAV and crawlers for comprehensive inspection. Then it was awarded by American Society for Civil Engineers 2025 Charles Pankow Award for Innovation. See, it is a wonderful thing. Combined together, both the flying and crawling activity. Heron and Omicron, autonomous ground vehicle and intelligent decision support tool for road and bridge maintenance, integrating digital twin and BEM. Integration into maintenance planning. Robotic inspection data is processed using AI and integrated into digital twin platform, supporting automated reporting, defect tracking, and predictive maintenance. See, one thing so far you might have noted it. that the data is voluminous. It is not possible to manage humanly. So AI is required even for processing. Once you convert the data into information, even then it is needed for classification and some prediction activity. So AI is becoming like a backbone of all these inspection systems. Second thing is that very often being told digital twin platform. Because it is not one technology you are using, you are trying to create the digital twin of the original structure, and you are trying to impose upon the data or the observation of various technology together, then try to validate each other, and then try to find out the final outcome. So these two things are everywhere reported. After that only it can be automated, the reporting, defect tracking, etc. can be done. So let's come to the digital twin and bridge monitoring model. The advantage of this thing is holistic asset management centralizes all the relevant data for life cycle management and decision making. As I told you, it is a virtual replica of the physical bridge, integrating the geometric model, sensor data, historical inspection record and maintenance action. Everything will be together. ब्रिज को मेंटेन करने के लिए हमने अभी तक क्या किया है वो भी इसमें कहीं ना कहीं हमें रिफ्लेक्ट करना पड़ेगा. Bridge information modeling extends bridge information management system to the infrastructure supporting collaborative design, construction, operation and maintenance. So ब्रिज के कंस्ट्रक्शन के नए ब्रिज के लिए अगर बात करें तो ब्रिज के कंस्ट्रक्शन के समय की सारी प्रैक्टिस को भी कैप्चर करना पड़ेगा. कहां पे क्या प्रॉब्लम हो गई थी ब्रिज बनाते समय, वो पॉइंट कहीं ना कहीं हमें रिकॉर्ड करके रखना पड़ेगा ताकि भविष्य में उस लोकेशन पे या उस प्रॉब्लम की वजह से कोई इशू आता है तो वी कैन इंटरप्रेट करेक्टली. I remember in the northern area, this Ganges irrigation canal system nearby Roorkee, today's IIT Roorkee, that time it was made as the engineer's office who was constructing that upper Ganga canal system. So in that there is a barrage. In barrage, for a particular pier, now this irrigation officials, they observed that the particular pier is started shaking. They got worried. They tried to find out what is happened, why it is happening. They are not able to get any relevant information. They are not able to find out what is to be done. Then some of the old engineer, they told that, sir, I heard that something is there in the drawing, etc. If we are able to trace out the old drawing. So they worked and they find out the old drawing. And in one of the drawing, it was written that in this particular barrage, this particular pier is expected to behave differently in due course of time. And if it behaves differently, then this action is to be taken because this is the approximation or this is the problem we faced here and we made some sort of solution to the problem at that time. And they also suggest what action is to be taken. So based on that, the today's field engineer applied and they are able to solve that problem. Means stabilize the structure. So what I mean to say that for For a new structure, if we maintain the record correctly and holistically, then it may be possible in future not to dig open and find out what happened, and based on the record itself we can say yes, there was a problem and this is a possible solution, and then we can do justice to maintenance system. So that is what is the data capturing is required. That is what is the exact digital twin. Otherwise, we had made the idealistic digital twin. So digital twin will also help enable the real-time monitoring, predictive analysis and simulation of the structure behavior. They are now increasingly integrated with artificial intelligence, IoT, cloud computing and augmented reality for enhanced visualization and decision support. So these things are happening in the world. Whether we are able to use it right now or not, but what are the advantages of digital twin? Holistic asset management centralizes all relevant data for life cycle management and decision making. Predictive maintenance supports forecasting of the deterioration and optimization of intervention schedule. Collaboration and visualization. This enhances stakeholders' engagement and transparency through interactive 3D model and dashboards. Cost saving. It reduces inspection, labor, repair cost and downtime through the data-driven planning. So, idea is that we can do a lot of experiments on the digital twin, which we cannot do otherwise on the real structure. Limitation, initial investment. Yes, it is costly. High upfront cost for modeling, sensor integration and platform deployment. It is again difficult if we do not embed the sensor into the structure. It can be done, but it is still better if we embed the sensor. Data integration, challenges in harmonizing diverse data source and format. Sensors, when they speak together, they talk together, they supplement each other. That's a data integration for the sensors. Yes, it is a challenge. Skill gap, require expertise in advanced modeling, data analytics and system integration. It's a big, you are basically entire communication network, signal processing, computing, all things you are putting together and then you are trying to make the model. So it is a multi-domain expertise required, and accordingly the cost. Some of the examples which has been done: Stone Arch and the Robert Street Bridges in USA. AI-powered digital twin reduces inspection time and cost, improved data quality and enabled remote condition assessment. Kentucky Bridge program in US, digital twin and 3D modeling cut survey time by 50% and saving enough money and accelerating infrastructure improvement. Germany's Autobahn bridges, digital twin integrated with AI-driven damage analysis and drone data improved inspection accuracy and enhanced predictive maintenance. Australia's Wadham's Road Bridge, fully digital workflow integrate design, geotechnical analysis, construction planning and maintenance forecasting, yielding significant cost and time saving. Somebody can say that Western and here it may be different, but when we wanted to lead the world, when we wanted to go ahead, rest of the West countries, then why not? Digital twins are central to model bridge management systems, supporting condition assessment, maintenance scheduling, risk analysis and regulatory compliance. AI-driven analytics and sensor data enable proactive interventions and resource optimization. It is very much written on the wall. today, maybe after 5 years, not far away. LiDAR, photogrammetry and 3D scanning for as-built models. LiDAR, we know, light detection and ranging, and the photogrammetry are non-contact method for generating high-precision 3D model for bridge structure. LiDAR uses laser pulses to create dense point clouds, while photogrammetry reconstructs geometry from overlapping images. Like I told you, in the one small video what we have seen, there are many number of triangles, squares, etc. They are all the points. So when we focus on the points with the help of a LiDAR, it is possible for us to fix the geometry accurately. All those points we capture it, we measure the location, and with the photogrammetry we can create a three-dimensional images. So with that thing, it is possible for us to make the a better model. UAV equipped with LiDAR and camera enable rapid comprehensive data collection. 3D scanning supports as-built documentation, defect mapping and integration into BRIM and digital twin platforms. So what is actually happening when we all put together all these sensor network and inspection methods together, we will be able to get a better platform to give us the desired results. What is the advantage? High accuracy, sub-centimeter precision. This is very important, sub-centimeter precision. Enable detailed condition assessment and modeling. Rapid data collection, UAV-based system cover large area effectively reducing survey time and labor. Integration with AI supports automated defect detection and cementing segmentation of structural components. What are the limitations? Cost. LiDAR equipments are expensive. Through operational saving accrue over time. बहुत सेम LiDAR सिस्टम से जगह जगह काम करेंगे तो हो सकता है वो मल्टीपल यूजेस की वजह से सस्ता पड़ जाए, लेकिन उसका यूज करना और उसके लिए एक्सपर्ट को लाना महंगा है. डाटा प्रोसेसिंग. Large data sets require robust storage and processing capabilities. Environment constraints, again vegetation, weather, access effect, data quality. So we need to be careful about all these things. Some of the examples. Maguire Bridge in Italy, UAV, LiDAR and photogrammetry produce a digital twin with 3 cm accuracy supporting maintenance planning and technical documentations. Parsons and Autodesk collaborations. So Autodesk, you know, AutoCAD. High resolution photogrammetry and reality capture streamlined creation of intelligent model for downstream bridge design and analysis. Bridge scan, Europe का है. Drone with laser scanning captured 3D topography data for bridge assessment, enabling deformation analysis and component extractions. How it can be integrated into model maintenance planning? 3D models are integrated into BIM and digital twin platform supporting defect mapping, structural analysis and life cycle management. Semantic segmentation and AI driven analysis enhances automation and scalability. कहने का माने कि डिफरेंट टेक्नोलॉजी का इस्तेमाल करके हम ज्यादा एक्यूरेटली, ज्यादा कॉन्फिडेंटली डिफेक्ट को एनालाइज कर सकते हैं, लाइफ एक्सपेक्टेंसी निकाल सकते हैं और मेंटेनेंस प्लानिंग को रिशेड्यूल कर सकते हैं. देन थर्मोग्राफी, acoustic emission and vibration based methods. Infrared thermography detects subsurface defects, delamination, voids, cracks by measuring temperature variation on the surface. Surface हीट एब्जॉर्ब करती है और वो हीट एब्जॉर्ब करने के बाद उसको वापस एमिट करती है. जहां पे मटेरियल नहीं है, वॉइड है, उसका हीट एब्जॉर्प्शन कम होगा. जब हीट एब्जॉर्प्शन कम होगा तो उसका हीट एमिशन भी कम होगा, अकॉर्डिंगली उसका टेम्परेचर जल्दी से कम हो जाएगा और अमाउंट ऑफ रेडिएशन, थर्मल रेडिएशन भी कम होगा, तो उसकी वजह से हमें हॉलो सरफेस पता लग जाती है, तो ये हेल्प करती है. देन acoustic emission, it monitors stress wave generated by crack initiation and propagation, enabling real-time detection of active detonation. इसको हम कहते हैं ना कि डॉर्मेंट क्रैक है या लाइव क्रैक है, तो लाइव क्रैक होगा तो हर बार लाइव क्रैक जो है acoustic emission देगा. It's just like that. If one human being got a problem and every time he walks it hurts, he will emit some sound. और कहीं चोट लगा था and that has already healed or it is not affecting his regular working, he keep on working. So that is how the active defects emit acoustics. Then vibration based monitors using modal analysis, natural frequency, damping ratio, etc. to assess structural integrity and detect changes due to damage. What are those things? Every system is having a fixed mass, it is having a fixed structural stiffness. Structural stiffness of a system depends upon its shape and size. If there is a crack in the structure, it reduces its shape and size at that particular location. Similarly, if the structure, or you can say other word, it can create a sort of hinge at that location. So its behavior changes. Depending upon the severity of defects, the behavior of the structure changes. If we are able to capture those things, then it is possible for us to monitor and pinpoint what are the defects. Again, it need to be, all these things need to be clubbed together with different type of other activities, other sensing devices, etc. Non-contact and rapid, it covers large area effectively without physical intervention. Sensitive to subsurface and active defects, supporting preventive maintenance. Enhanced defect classification and trend analysis. What are the limitations? Environmental sensitivity. Results depends on ambient temperatures, solar loading and material property. Depth resolution. Limited ability to determine defect depth, especially with the infrared, what is that? Thermography. सबसरफेस डिफेक्ट को ले लेगा, लेकिन अगर हमारा स्ट्रक्चर 1 मीटर मोटा है तो शायद नहीं पकड़ पाएगा. बट टिपिकली वी डू नॉट हैव दैट टाइप ऑफ थिक स्ट्रक्चरल एलिमेंट्स नॉर्मली. Noise and interpretation. Acoustic emission is sensitive to external noise. Data analysis is required exercise. It is capturing the acoustics, noise only, sound waves. तो अगर बाहर से भी साउंड आ रही है तो उसको पकड़ लेगा ये. वो दोनों नॉइस और जो स्ट्रक्चर की नॉइस है, स्ट्रक्चर का जो साउंड है उसको मिक्स करके कंफ्यूज हो जाएगा, तो उसको सुधारना जरूरी है. डोंगाई बेस में ड्रोन बेस्ड infrared thermography and AI segmentation enabled rapid accurate determination, delamination detection. Highway Laboratory USA UAE based passive IRT detection detected delamination in RC bridge deck with the combined active passive method recommended for comprehensive assessment. तो एक्टिव पैसिव का माने, पैसिव का माने दूर से उसने फोटो खींच लिया, एक्टिव का माने सेंसर लगा हुआ है जो हर बार चेक कर रहा है लोड आने पे. Acoustic emission testing यूएस में किया गया. एई सेंसर मॉनिटर्ड कोरोजन इंड्यूस्ड माइक्रो क्रैकिंग इन हाईवे ब्रिजेस इनेबल अर्ली. इट्स वेरी इंटरेस्टिंग. Reinforcement bars are corroded and because of corrosion volume is increased, and because volume increase the concrete around the reinforcement is pushed apart, and if it cracks, then as the corrosion increases, it further push away and further crack develop. So as and when the crack develop, acoustic emission will tell, delamination is possible. कहां कहां पे हो रहा है, इसी को अगर हम और किसी और मेथड से पैरेलली कंफर्म कर लेते हैं तो क्लियर हो जाएगा कि कहां पे प्रॉब्लम आ रही है. Thermography and AE data are integrated into digital twin platform and maintenance decision support system supporting risk-based prioritization and regulatory compliances. तो इस टाइप के ये तमाम सिस्टम्स जो हैं, एडी करंट, अल्ट्रासोनिक, फेज अरे एंड रोडियोग्राफी, ये सारे के सारे स्टील से रिलेटेड आइटम है. एडी करंट डिफेक्ट्स detects surface and near surface cracks in steel using electromagnetic induction, effective even though coating is there. पेंट का कोट है, उसके बाद भी एडी करंट काम करेगा. Phased array, advanced phased array with multiple transducer for volumetric imaging and precise defect sizing, validated as an alternative to radiographic for weld inspection. ये एक इंपॉर्टेंट चीज निकल के आ रही है. Radiography, X-ray, gamma ray imaging reveals internal flaw primarily in the steel structure. क्योंकि रेडियोग्राफी के अपने हजार है, इसलिए इसको यूज कर पाना मुश्किल हो रहा है, लेकिन पाउट के आने के बाद ये प्रॉब्लम थोड़ी थोड़ी सॉल्व हो रही है. इसके एडवांटेज क्या है? हाई सेंसिटिविटी, डिटेक्ट स्मॉल एंड कॉम्प्लेक्स डिफेक्ट्स विद हाई रेजोल्यूशन, नॉन इन्वेसिव, प्रिजर्व स्ट्रक्चरल इंटीग्रिटी एंड मिनिमाइज डिसरप्शन, स्टैंडर्डाइजेशन मेथड्स आर कोडिफाइड इन इंटरनेशनल स्टैंडर्ड. ये सारे के सारे धीरे धीरे कोडिफाई हो रहे हैं. तो बाहर तो हो चुके हैं, हमारे यहाँ भी रोड कांग्रेस के या रेलवे के अगर आ रहे हैं तो मिल जाएंगे समय के साथ. Then limitations, surface preparation. Some methods require clean, accessible surface. Coating may affect like pout. हाँ, साल विद इन ईयर अभी सरफेस के नीचे कोरोजन चालू नहीं हुआ तो पाउट भी काम करेगी, लेकिन अगर मेटलाइजिंग के नीचे कोरोजन शुरू हुआ तो पाउट काम नहीं कर पाएगी. सेफ्टी एंड कॉस्ट, रेडियोग्राफी इन्वॉल्व्स रेडिएशन हैजार्ड, एक्सपर्टाइज रिक्वायर्ड, इंटरप्रिटेशन ऑफ रिजल्ट डिमांड्स स्किल, ऑपरेटर एंड कैलिब्रेशन. तो बिना उसके काम नहीं होगा, अदरवाइज वी मे इंटरप्रेट इनकरेक्टली. फेडरल हाईवे एसोसिएशन ऑफ यूएसए पाउट वैलिडेट एज एन अल्टरनेटिव टू रेडियोग्राफिक फॉर वेल्ड इंस्पेक्शन विद स्ट्रॉन्ग कोरिलेशन इन डिफेक्ट साइजिंग. तो इनके कोड बना दिए हैं, हो सकता है भविष्य में अपने हाईवे में भी लोग कुछ काम कर रहे हैं पाउट पे. अगर वो आ गया है और हम उससे डिफेक्ट साइजिंग कर पाते हैं तो शायद रेलवे में भी हो जाएगा. एथर एनडी यूके ने एडी करंट वेल्ड प्रोब एनेबल एफिशिएंट इंस्पेक्शन ऑफ कोटेड स्टील वेल्ड्स, रिड्यूसिंग टाइम एंड कॉस्ट कंपेयर टू magnetic particle inspection and dye penetrant methods. NDT, these data used to calibrate digital twin and FEM model and inform the risk-based maintenance prioritization. So ये typically these are also like an NDT data. So उसी की तरह से ये भी काम करते हैं. Another method is ground penetrating radar and rebar detection system. So GPR is high frequency electromagnetic pulses to detect the rebar, void, delamination and moisture in concrete bridge decks. तो ये काफी चीजें पकड़ में आ जाती हैं इससे. और various automated algorithm with the AI modeling. It can process rebar diagrams to identify hydroprophic pattern indicative rebar and defects. तो इससे क्या होगा कि सरफेस में ये निकाल पाएंगे कि कहां कहां पे कोरोजन के चांसेस हो रहे हैं, कहां कहां पे रीबार के लोकेशन है और कहां कहां कोरोजन हो रहे हैं. तीन चीजों को अगर हम मिला के देख पाएंगे तो हम डीलैमिनेशन जैसी चीजों को पकड़ पाते हैं. तो इसके क्या एडवांटेज है? रैपिड एंड नॉन इन्वेसिव स्कैन लार्ज एरियाज क्विकली विदाउट डैमेजिंग द सरफेस. हाई स्पेक्ट्रल रेजोल्यूशन एक्यूरेटली लोकेट rebar and assess corrosion induced damage. Integration with AI automates defect detection and mapping, improve scalability and consistency. जल्दी करेगा और ये नंबर ऑफ ब्रिजेस पे लिया जा सकता है, इसकी लर्निंग भी फास्ट हो रही है. एक ही चीज, दो ही चीज पकड़ रहा है ये, लेकिन अच्छा पकड़ रहा है. लिमिटेशन क्या है? इंटरप्रिटेशन कॉम्प्लेक्सिटी. डाटा एनालिसिस रिक्वायर्ड एक्सपर्टाइज. एनवायरमेंटल फैक्टर अफेक्ट द रिजल्ट, लाइक क्रोजन वगैरह हो रहा है या मॉइस्चर है, तो दैट में टेम्परली अफेक्ट द क्वालिटी ऑफ डाटा. Material sensitivity, conductive material and the moisture can reduce the penetration and accuracy. Limited open source database, open source data set hinder AI model development and benchmarking. तो जितना ज्यादा काम होगा उतना बढ़िया रिजल्ट आने की संभावना है, लेकिन हाईली एक्सपर्टाइज्ड एरिया है तो लोग भी उसी हिसाब से कम है. एंड देन अगेन कॉस्ट भी प्रिवेंट करती है. Tom's Creek Bridge USA में automated GPR analysis accurately identified rebar depth and spacing, improving speed and reliability over manual interpretation. You only look once. Space GPR analysis, deep learning model trained on synthetic and real GPR, automated rebar detection, improving scalability and reducing manual annotation results. Integration into maintenance planning. GPR data is integrated into BRIM and digital twin platform, supporting defect mapping, structural analysis, and life cycle management. AI-driven analysis enhances automation and scalability. Okay. So, any questions so far? Anybody else? देखो आपको चैट में देखो
क्वेश्चंस नहीं है सर.
ओके,
आप अनाउंस कर दो क्वेश्चन के लिए.
सो अगर आप लोगों के कोई क्वेश्चंस हैं तो यू कैन टाइप इट इन द चैट बॉक्स एंड वी कैन क्लब टुगेदर एंड ट्राई टू डिस्कस अगेन. टॉपिक इज comparatively new. It is not readily being used in our system, so it still requires a lot of discussion. Okay, let's go further. Comparative analysis of various technology. Like see the drone, AI based analysis, SMH, etc. So we have that technology here, and initial cost, if you see that the cost of drone UAV and NDT is comparatively less high, or you can say other than these two the cost is high, and because of high cost they are not really being utilized. Then operational cost अगर देखा जाए तो ड्रोन और एआई बेस्ड की ऑपरेशनल कास्ट एक बार ट्रेंड हो जाने के बाद एआई बेस्ड एनालिसिस की ऑपरेशनल कास्ट कम हो जाएगी. इनिशियल कास्ट ज्यादा है लेकिन ऑपरेशनल कास्ट कम आ जाती है. लेजर क्लीनिंग एंड डिजिटल ट्विन, अगेन डिजिटल ट्विन उसी में चला जाता है. एक बार मॉडल बन जाने के बाद फिर उसमें बहुत ज्यादा मेहनत नहीं करनी पड़ेगी अनलेस अंटिल देयर इज अ चेंज इन द मॉडल. स्केलेबिलिटी देखते हैं तो चूंकि कॉस्ट हाई है, कॉस्ट लो है इसकी, इसलिए ड्रोन और रैपिड है तो ड्रोन और एआई बेस्ड सिस्टम हाई हो जाते हैं, और उसी तरह डिजिटल ट्विन भी हाई होगा क्योंकि एआई बेस्ड डिजिटल ट्विन मोर और लेस सेम लाइन पे जाएंगे. एक्यूरेसी हम देखते हैं तो एआई बेस्ड एनालिसिस और डिजिटल ट्विन की एक्यूरेसी बहुत ज्यादा है. क्यों मल्टीपल सिस्टम को यूज कर लेता है, रिजल्ट को वेरीफाई कर लेता है. लिमिटेशन कहां आती है? ड्रोन में वेदर, रेगुलेटरी एंड बैटरी लाइफ. स्ट्रक्चरल हेल्थ मॉनिटरिंग सिस्टम में इंस्टॉलेशन, डाटा मैनेजमेंट. एनडीटी में एक्सपर्टाइज, इक्विपमेंट कॉस्ट, एनवायरमेंटल सेंसिटिविटी. रोबोटिक्स में मोबिलिटी, पावर कॉस्ट, लेसर. और डिजिटल ट्विन में डाटा इंटीग्रेशन. सिमिलरली एआई बेस में डाटा क्वालिटी, एक्सप्लेनेबिलिटी एंड कंप्यूटेशनल रिसोर्सेस. तो ये जो चीजें हैं एआई में और डिजिटल ट्विन में जो अभी तक हम लोगों ने देखा है उसको एक बार रिपीट कर लेते हैं. ड्रोन के की फीचर क्या है? हाई रेजोल्यूशन कैमरा, लिडार, थर्मल सेंसर, एआई इंटीग्रेशन होगा. advantage, accessibility, safety, efficiency, data quality, limitation, weather, regulation, battery life, subsurface limitation, real world application के कुछ एग्जाम्पल थे यहाँ पे. AI बेस्ड सिस्टम में CNN, YOLO, फास्टर, RNN, सेमेंटिक सेगमेंट इसके फीचर्स हैं, हाई एक्यूरेसी है, ऑटोमेशन, पीरियोडिक एनालिसिस है, डाटा क्वालिटी, एक्सप्लेनेबिलिटी, कंप्यूटेशनल रिसोर्सेस, ये इसकी लिमिटेशन है, इतना आसान से नहीं हो पाएगा. स्ट्रक्चरल हेल्थ मॉनिटरिंग सिस्टम, स्टेन गेजेस, एक्सेलेरोमीटर, IoT, डैशबोर्ड्स एक्सेट्रा, कंटिन्यूस मॉनिटरिंग, डाटा ड्रिवन डिसीजन, इंस्टॉलेशन, डाटा मैनेजमेंट एंड बैंडविड्थ इज द लिमिटेशन. डाटा सारा का सारा फ्लो करके जो सेंट्रल प्रोसेसिंग यूनिट या ऑफिस है वहां नहीं पहुंचेगा तो कुछ नहीं कर पाओगे. NDT, अल्ट्रासोनिक फेज एरे, रडार, थर्मोग्राफी, acoustic emission, advantage, internal defect detection, non-invasive, qualitative, expertise, equipment cost, environmental sensitivity. If you say robotics, crawler, manipulator, hybrid UAV, advantage, safety, coverage, AI sensor integration, limitation, mobility, power cost. Cost ज्यादा होगी, पावर की रिक्वायरमेंट है तो बहुत देर तक काम नहीं कर पाएगा. लेजर क्लीनिंग, high power beam, portable device, advantage, precision, environmental benefit, operational flexibility, initial cost is very high, operator training is necessary and surface preparation is required. Digital twin, 3D model, sensor data, AI, cloud, ये इसकी जरूरी है. एडवांटेज क्या है? होलिस्टिक मैनेजमेंट, प्रेडिक्टिव मेंटेनेंस, विजुअलाइजेशन. Initial investment in data integration is high. Gaps are there. It cannot be easily used. LiDAR, photogrammetry, UAV based scanning, 3D modeling, high accuracy, rapid data collection, AI integration. ये तो एडवांटेज हो गए, लेकिन कॉस्ट ज्यादा है. डाटा प्रोसेसिंग, एनवायरमेंटल कंस्ट्रेंट्स जो ड्रोन में है वो इसमें आ जाते हैं. डाटा मैनेजमेंट के लिए क्लाउड प्लेटफॉर्म चाहिए, डैशबोर्ड और मोबाइल ऐप में आएगा. सेंट्रलाइज एक्सेस, ऑटोमेटेड रिपोर्टिंग, प्रेडिक्टिव एनालिसिस करेगा डाटा को यूज करके. लिमिटेशन, सिक्योरिटी ऑफ डाटा, प्राइवेसी, एडॉप्शन बैरियर्स, ये सारी चीजें जो काम को स्लो करते हैं. जितना ज्यादा डाटा सिक्योर करने की कोशिश करेंगे कि अल्टीमेटली ट्रांसमिट तो हो रहा है, कहीं जमा तो हो रहा है, वो सारी चीजें जो है कंस्ट्रेंट लाती है. क्योंकि डाटा के साथ साथ आपको सिस्टम भी लाना पड़ेगा जो यहाँ पे एनालिसिस करके देगा. खाली डाटा स्टोर करने से नहीं होगा, क्योंकि अल्टीमेटली अगर डाटा आपने ट्रांसफर किया तो डाटा फिर चला गया, फिर तो जो उसको यूज करने वाला सॉफ्टवेयर है वो भी आना चाहिए. अभी तक अगर कुछ क्वेरी है तो उसको टाइप कर दीजिएगा. अदरवाइज देयर आर फ्यू केस स्टडीज जो ऊपर हम लोगों ने बाद में नाम लिया था कि इटली में क्या हुआ, USA में क्या हुआ, तो उसकी कुछ एक केस स्टडी है और उसने बड़ा सिंपल मेथड में दिया, बहुत ज्यादा डिटेल में मैं नहीं गया हूं. बाकी डिटेल में जाने के लिए हर केस स्टडी को फिर से पूरा डिटेल में पढ़ना पड़ेगा. जेनोवा मोरेंडी ब्रिज इन का US का, इसका इटली का कोलैप्स का केस है. 43 facilities was attributed to inadequate inspection, corrosion of steel cable and insufficient maintenance by privatized operator. तो क्या मिला? Inadequate inspection, corrosion and insufficient maintenance by private operators. Investigations highlighted the need for a stricter standard, increased inspection frequency, comprehensive record keeping and adoption of modern material and technology. This tragedy prompted regulatory reforms and accelerated the adoption of digital tool for inspection and maintenance across Europe. तो हमें दूसरों के फेलियर के एग्जाम्पल से अपने चेता लेना चाहिए और इसको अडॉप्ट करना चाहिए. Stone Arch and Robot Street Bridge in USA, Collins engineers implemented AI-powered digital twin, reducing inspection time by 20%, labor cost by 10 to 15%, and improving data quality for Minnesota Department of Transport. The approach enabled remote condition assessment, predictive maintenance, and substantial cost saving. ये सोचना कि स्टील या PSC में ही करना है, नहीं, स्टोन आर्च में भी इन्होंने काम करके कुछ ना कुछ बेनिफिट लिया. कैंटिकी ब्रिज प्रोग्राम यूएस का, डिजिटल ट्रांसफॉर्मेशन ऑफ ब्रिज सर्वे, कट सर्वे टाइम बाय 50%, सेविंग ह्यूज मनी एंड एक्सेलरेटिंग इंफ्रास्ट्रक्चर इंप्रूवमेंट फॉर रूरल कम्युनिटीज. डिजिटल ट्विन एंड 3D मॉडलिंग enabled rapid recovery and rebuilding after devastating flood in 2022. So की सारी चीजें पर मौजूद है. Shanghai with China drone-based edge device perform real-time crack detection using You-Look Only Once version 8 and Deep Lab version 3, achieving high accuracy and rapid inference. The system reduced risk associated with high altitude operations and enabled efficient maintenance planning. Germany's Autobahn, digital twin integrated with AI-driven damage analysis and drone data improved inspection accuracy and enabled predictive maintenance. Demonstrated in the Twin City and Die Autobahn bridge. Crack and multitask integration algorithm. The color gradient on the right represent the pixel scale width distribution at the skeletal points. इसमें ये देखेंगे हम, ओरिजिनल इमेज ये लिया गया है, इस इमेज की प्रोसेसिंग करके पूरी इमेज में से ये पर्टिकुलर एरिया हमने काट के निकाला. तो पूरी इमेज में से ये एरिया निकालना है. निकालने के बाद उसको सॉफ्टवेयर के हिस्से में ले जाना है. उसके बाद उसको जो हमने चेक किया, ये देखा कि थर्मल इमेज से क्या हो रहा है, स्ट्रक्चरल चेंजेस, ये स्ट्रेस स्ट्रेन से क्या बिहेवियर आ रहा है. इन सब चीजों को मिला के फिर हम इस क्रैक को आइडेंटिफाई कर पाते हैं. लाइव है, डेड है, बढ़ रहा है, घट रहा है, स्ट्रक्चरल स्ट्रेंथ में क्या अंतर आ रहा है, वगैरह वगैरह. ये इसी का डिटेल्ड वर्जन है, कैसे क्रैक मिला, कैसे हमने एरिया देखा उसका. ये जो स्टोन आर्च ब्रिज का बात किया था, उसका ये जस्ट इमेजिन दिस मेनी नंबर ऑफ द डाटा पॉइंट्स हैज बीन scattered all over surface of the stone arch bridge and हर पॉइंट का मॉनिटर किया गया. मॉनिटर करने, इमेज के बेस्ड है ये. मॉनिटर करने के बाद हर पॉइंट में देखा गया कि किस तरह से बिहेवियर हो रहा है, सही राइट है या रॉन्ग है. फिर उसके बाद इस ब्रिज को मेंटेन किया गया. ये ड्रोन है, ये ब्रिज दिखा रहा है कैसे हमने डाटा कैप्चर किया इसका. ब्रिज क्रैक डिटेक्शन के लिए ड्रोन का इमेज एक्विजिशन किया गया. उसके बाद यूलो बेस्ड क्रैक ऑपरेशन में इससे एनालिसिस किया गया. फिर उसके बाद दो तरह से लिया. एक तो मॉडल को हमने सुधारने की कोशिश किया, और मॉडल को सुधारने से हमें जो है क्रैक को आइडेंटिफाई करके लोकेट करने में मदद मिली. दूसरा क्या किया हमने, लोकल रिजल्ट्स को करके उन्हीं इमेज को देखा जिनकी जरूरत थी, उनको लेबलिंग कर दिया, और उसके बाद जो रिक्वायर्ड इमेज है उनको ही आगे लाके काम करने की कोशिश किया गया. उसके बाद जब ये सारी चीज हो जाती है, हमें समझ में आने लगता है, देन डाटा को आगे बढ़ा के क्रैक विड्थ की एनालिसिस करेंगे, और उसमें हमने स्केल पे ये नापने की कोशिश किया कि क्या हमारी क्रैक की साइज और मींस विड्थ एंड लेंथ आती है. उसके बाद डिपेंडिंग अपॉन द साइज अलर्ट होगा या रूटीन मेंटेनेंस के लिए वो चला जाएगा. स्ट्रीमलाइन ब्रिज इंस्पेक्शन, इन्हीं सब चीजों में अगर हम अपने सिस्टम को जब स्ट्रीमलाइन करने लगेंगे तो कैसे होगा. जो बातें मैंने बोली बीच बीच में, उसको कैसे हम कोलेट करते हैं. तो ये सारा का सारा डाटा जो है कैप्चर किया गया, ग्राउंड कंट्रोल से यूएई से किया गया, डाटा सर्वर रख के ब्रिज से सारा डाटा कैप्चर करके एक जगह जमा कर लिया. उसके बाद डाटा प्रोसेसिंग मॉड्यूल बनेगा जिसमें सारा फोटो, वीडियो, जीपीएस, सारा डाटा आ जाएगा. उसके बाद 3D मॉडल उसका बनाएंगे, उसका एफई एनालिसिस मॉडल बनाएंगे, उसमें ये जो डिफेक्ट डिटेक्शन है उसके साथ इंटीग्रेट करेंगे. फिर हम एनालिसिस करके देखेंगे कि डिफेक्ट के लोकेशन पे स्ट्रेस और स्ट्रेन का बिहेवियर कैसा है. उससे हमें पता लगेगा कि डिफेक्ट हमारा लाइव है, आगे प्रॉब्लम क्रिएट करेगा, स्ट्रक्चरल डिफेक्ट है या सिंपल स्ट्रक्चरल डिफेक्ट नहीं है। और ये सारा का सारा डाटा हमें कहीं ना कहीं सर्वर सिस्टम में रखना पड़ेगा, और उसके बाद ये जो है हम किस तरह से इसको हैंडल करना चाहते हैं, मोबाइल में, टैबलेट में या कंप्यूटर पे बैठ के करना चाह रहे हैं, वो सारा का सारा काम किया जा सकता है। तो ये एक बेहद स्कीम बनानी पड़ेगी और उस स्कीम के बेसिस पे सारा काम होगा। तो सुबह सबसे पहले वी डिस्कस अबाउट द कैसे हम मॉडलिंग करते हैं। तो इसमें है 3D पॉइंट एंड क्लाउड मॉडल, फोटोग्रामेट्री, लिडार एंड फ्यूजन स्ट्रेटजी। तो क्या किया इसमें, लिडार से हम सारी लोकेशन कैप्चर करते हैं, फोटोग्रामेट्री से हम उसकी 3D व्यू बना लेते हैं। अब इनको जब सुपर इम्पोज करते हैं तो हमें पता लगेगा कि कौन सा पॉइंट किस इमेज पे, मतलब इमेज का कौन सा पॉइंट कहां पे लाई करता है स्ट्रक्चर एलिमेंट पे। जब वो कर लेते हैं उसके बाद हमें रियलिस्टिक मॉडल मिलके फिर हम फर्दर उसकी एनालिसिस वगैरह कर पाते हैं। इसी के साथ अगर हम आगे एफईएम को ऐड कर लेते हैं, इसी के साथ हम और सेंसर को ऐड कर लेते हैं, तो हम यहां चले आते हैं इस केस में। तो दिस इज व्हाट इज something new what I wanted to discuss today. If anything you need to discuss or anything you want me to tell or you want me to decide the future or the next webinar or any related topic.
नमस्कार सर, डिप्टी सी डिजाइन बोल रही हूँ एनडब्ल्यूआर से।
बोलिए मैडम।
सर हमारे यहाँ पे अभी हम लोगों ने ड्रोन और लिडार दोनों से मिलके एक सर्वे करवाया था।
वेरी गुड।
तो सर उसमें हमें डेटा आ गया सारा पॉइंट क्लाउड पे, और 3D मॉडल भी उसने डेवलप कर दिया था।
ओके।
और सर उसने एक्चुअली जो ओरिजिनल डायमेंशन थी जीएडी दिया था, उसके कंपैरिजन में डायमेंशंस और ट्विस्ट वगैरह कैलकुलेट किए थे सर।
ओके।
बट सर आज की डेट में वो मतलब इनिशियल से कंपैरिजन का कोई मतलब यूटिलाइजेशन अभी क्लियर हो नहीं पा रहा कि एग्जिस्टिंग स्ट्रक्चर में हमने कर तो लिया है सारा डेटा, बट नेक्स्ट टाइम के लिए।
इसमें मैडम एक चीज आप अभी बता सकते हैं कि जैसे अभी एक एनालिसिस में किसी ने कहा कि उसकी एक्यूरेसी 3 सेंटीमीटर की थी, तो चूंकि आपने इसमें लिडार भी ले लिया है और उसके अपने स्ट्रक्चरल ड्राइंग से भी उसको कर लिया है, तो क्या एक्यूरेसी आपकी इससे बेहतर आई है या इससे खराब आई है?
एक्यूरेसी तो ठीक है सर, हमारी 5 सेंटीमीटर का आता सर 50 में।
तो उन्होंने 3 सेंटीमीटर कहा, आपकी 5 सेंटीमीटर आ रही, तो इसका माने वो कंपेरेबल टेक्नोलॉजी है और हम इसको, आप भी इसको कोलैबोरेट कर रहे हैं, इस तरह से हम काम कर सकते हैं। वेरी गुड।
बट इसमें डेटा का यूटिलाइजेशन क्या रहा, मतलब हमने कंपैरिजन तो कर लिया।
नहीं डेटा करेक्ट, डेटा का यूटिलाइजेशन क्या है कि अभी आपने किया, आपका ये ब्रिज कितना पुराना है?
ये सर 15 साल पुराना है सर।
ओके। तो इसमें इशू क्या हो गया कि 15 साल पुराना है, बेसिकली बेस लाइन आपकी 15 साल के बाद बनी।
यस सर।
अब इसका डेटोरिएशन अगर इसमें किसी तरह से मिलता है 5 साल बाद डाउन द लाइन, तब आपको ये समझ में आएगा कि इसमें खाली लिडार और फोटोग्रामेट्री यूज करके आपको समझ में आएगा कि क्या हो रहा है। लेकिन इसी के साथ अगर इसमें कुछ सेंसर भी लगा देते हैं जो स्ट्रेस या स्ट्रेन को कैप्चर करके कुछ और इंफॉर्मेशन दे पाएंगे, और उन चीजों को अगर हम देख लेते हैं तो हमें समझ में आ जाएगा कौन कौन से क्रिटिकल लोकेशन पे हमने सेंसर लगाए हैं, उनका बिहेवियर कैसा है। अगर उन क्रिटिकल लोकेशन का बिहेवियर भी अच्छा है सेंसर से, तो इसका माने आज की डेट में उस स्ट्रक्चर को कोई इशू नहीं है।
ओके सर,
थोड़ा और आगे
दोनों अलग अलग कर दिया था, इंस्ट्रूमेंटेशन हमने अलग किया और सेंसर्स लगाए उसमें हम लोगों ने, और ये वाला अलग किया था। तो दोनों एक दूसरे से क्लब नहीं है, दोनों सेपरेट सेपरेट ब्रिज के लिए किया है, 2 टेंडर।
हाँ तो ठीक है। अभी हम लोग जो है टेक्नोलॉजी टेस्टिंग के फेज में है।
जी सर।
आपने टेक्नोलॉजी को यूज किया अभी, और ये है ना, जैसे मिठाई की दुकान पे जाके सैंपलिंग करते हैं,
जी सर।
तो आपने अभी टेक्नोलॉजी का टेस्ट लिया है। तो ये इसलिए अच्छा है, आपका एफर्ट इसलिए बहुत अच्छा है कि जो हमारे यहाँ पे और भी लिसनर्स हैं उन लोगों में, उनको ये समझ में आएगा कि इस तरह की टेक्नोलॉजी अवेलेबल हो गई है इंडिया में, और हम लोग किसी रेलवे ने उसका इस्तेमाल किया है, तो जैसे जैसे हर रेलवे में मान लीजिए 2-2, 3-3 केस हो जाते हैं, तो हमारे यहाँ बहुत से पैरेलल केस स्टडी मिल जाएंगी और हमारा कॉन्फिडेंस बढ़ जाएगा इन टेक्नोलॉजी को यूज करने के लिए।
ओके सर।
तो रियली कुडोज टू यू, आपने एक अच्छी टेक्नोलॉजी का यूज किया।
मतलब सर नेक्स्ट टाइम ठीक रहेगा सर डेटा। सर
हाँ,
हमने
बिल्कुल।
क्रिस में भी बात किया था, वो एक सॉफ्टवेयर डेवलप कर रहे हैं इसके रिगार्डिंग, जिसपे कि सर क्रिस में मतलब सी है सर एनआर में। हाँ सर, वो एक सॉफ्टवेयर डेवलप कर रहे हैं, जैसा ब्रिज मैनेजमेंट सिस्टम है सेम ऐसा ही, उसमें ये 3D मॉडल डेवलप करके और उसमें इनकॉर्पोरेट कर दिया जाएगा, तो बाद में कभी भी किसी को देखना है तो वो शायद उसी से लिंक हो पाएगा।
हाँ, तो यही चीज है, इंपॉर्टेंस ये है कि वो जो डाटा आज कैप्चर किया बेसलाइन डाटा, वो कहीं ना कहीं हमारे पास जमा रहना चाहिए ताकि भविष्य में हम उसका इस्तेमाल कर पाएंगे। इमीडिएट यूज नहीं मिलेगा, ये आपका कहना सही है कि अभी क्या, तो यस मैंने खर्चा कर
हमें समझ नहीं आया कोई यूज है, मतलब फ्यूचर में जाके ठीक है कि हम कंपैरिजन कर पाएंगे, बट आज की डेट में तो वो डेटा कैप्चर हुआ है बेसिक।
करेक्ट मैडम, कम से कम आपने ये टेक्नोलॉजी को प्रूव तो किया, जो हम थ्योरेटिकली कह रहे थे 3 सेंटीमीटर है किसी और के एक्सपीरियंस के बेस पे।
यस सर।
एनीवन एल्स? किसी को और कुछ शेयर करना है? We are discussing. It is nothing like that I know you know or I don't know you don't know type of thing.
Sir, good afternoon. This is Scenery and Bridges from Vijayawada South Central Railway.
या प्लीज टेल मी। आप लोग अपने वीडियो फीड ऑन कर सकते हैं, अब इसमें डिस्कस नहीं कर रहे हैं तो वी कैन यूज दैट थिंग। ओके, बोलिए।
Sir, recently we are under the process of राजमंड्री गोदावरी केबल आर्च ब्रिज केबल रिप्लेसमेंट का काम चल रहा है सर।
ओके
Godavari Arch Bridge is a robotic and new technology we are utilizing. In that, we want to do the real-time structural health monitoring system for monitoring of the cables.
Okay.
Replaced cables.
Okay.
So for that reason, we had recently, my CBE sir and myself, we had 15 days back, we have visited the Agarwal and the Chana Bridge also, what the instrumentation they are using, how DHMS, what the methods they are using. And real-time structural health monitor and we have the some source of some literature or some guidance for Indian Railways. इसमें who have to contact sir, either RDSO or Chris or what? किसको है what? Any IRICEN is
really
giving any
really speaking
कोई
रियली स्पीकिंग इसमें हम सभी लोग जो है भी अंधेरे में हैं कि जब तक इसमें हम लोग काम नहीं करेंगे, अनलेस वी डू समथिंग, वी विल नॉट हैव दैट मच ऑफ द कॉन्फिडेंस ऑफ टेलिंग इट. Like you have gone to USBR Ranjikhed and Chenab, that area.
Yes,
so
sir.
there they had already deployed some of the sensing equipment and arrangement. Still, that entire system is totally controlled by that agency.
Yes, private agency.
And those private agency, if I am not wrong, you can correct me, they are doing the job for past several years, maybe 10 years.
Yes.
So sensing data is not one time job. It requires baseline setting, and then it need to monitor and then see that what is happening. See, this entire whatever we discussed today, it is not going to help you the way we are maintaining our structure, say oiling, greasing, say painting, say rust removal. All those things still has to be done.
Yes, sir.
So those type of manual thing will not be removed. What will be help? We will get it. Like we had got some problem because of the fatigue failure or the failure of the bridges and catastrophic failure like collapse, all that type of thing. So all those things we get a pre-warning.
Yes.
So it is to prevent a disaster. Like rightly you have told, if you have to assess the health of the cable,
sir,
then you require a typical type of sensor which is able to monitor the corrosion in the cable.
Yes.
It shall also able to monitor the thinning of the cable. It shall also able to monitor the reduction in the stress in the cable. It shall also able to monitor the connection of cable at the tower and at the deck. See, all the anchor zone, I mean. So all those things monitoring, we require a specialized instrumentation scheme. For example, stress or strain in a cable that can be monitored by deploying vibration sensor on the cable. Like a musical instrument, you are using guitar, sitar or anything, the moment you tighten that wire, its vibration frequency changes.
That is with the accelerometers.
Yes. So if that type of thing is there, then its a natural frequency because of wind blow will change. If we are able to capture that data, then we can also capture it. What is the likelihood of tension in the cable? And if there is a release in the tension, that makes that cable is not able to support the desired load.
Yes.
You're getting that point?
Yes.
If we are able to monitor along with vibration data corrosion in the cable and we understand how much percentage of diameter is corroded, so we can able to say how much thinning happened. So like that 3-4 thing, if we are able to do it, then it is possible for us to estimate the extent of health of that cable arrangement. So it has to go in that way, because every thinking, if you say that Anjikhet, they have done some arrangement. Anywhere else, no, we don't have experience. Some arrangement is being done in the Kolkata, that old Vidyasagar Setu or something. Something they are doing it. Like that, you can say there are many, really few number of bridges where work is being done or some instrumentation is done. So, yes, so if you are able to do, you will be one among the pioneers who has done this thing, and then like that the technology adoption will develop.
Yes, sir. We are on the way, sir. Myself and my CV, sir. Yes, sir. We hope how much we will succeed this one.
Yeah. My best wishes to you. See, always in the beginning we all have apprehension for success or failure, but the right thing is to do it.
Yes, sir.
And do it and then share with others, so that everybody's expertise will able to utilize it. We can make others aware how it is being done, and everybody can think. See, like today's presentation, I collected the data from various sources, then summarized and given it. So it will be a sort of triggering.
Yes, sir.
In a way, it was a very preliminary thing. It was a very, you say, technical point of view, content is very small. It is only telling you what are the things available. So with that thing, if you are able to think it, I think in future somebody will really discover and say that like this, like you are doing working, all the madam has told they have done some system. So this thing will come up. Yes.
Sure, sir. Sure. Thank you.
काम करते हैं इस तरह के पिघले ब्रिजेस में, तो उसी इनिशियल टाइम में डिजाइनर या कंसल्टेंट सर उसी टाइम में डिजिटल ट्विन क्यों नहीं बना ले सर, कंस्ट्रक्शन फेज के बाद ही?
Like I tell you, one more example I'll share you. Some of the faculty from IIT, they were working on a bridge in I think Mumbai, Central Railway. So at the time of construction, they embedded many number of sensor into that particular girder, PSC girder, and they monitor for substantial time. They concluded good information that there is not much change because of the heat of hydration. So there is a good conclusion that heat of hydration has not created problem in that type of thin concrete structures. So it is always good if we do the sensing system for the structure right at the beginning, at the time when the structure is being constructed. And that time itself, we can make out the, I should say, a digital twin or a partial digital twin at that time. So it depends how the technology flow in the system, we may be able to do it.